Hello, sir.
Hello there.
Yeah, should we wait or we can start?
Um, it's up to you. We're still expecting more people, I gather.
Yes, sir, you can start like by the time the people will join.
Okay, Doug. All right. So, do you want to do some sort of introduction or something?
Hello, sir.
Hello.
Sir, we can. I hope like all the teams have joined,
Okay.
and at the time or like those who are remains, they can join later.
Okay. Do you want to do some introduction? Hello?
Good afternoon to all. Today we are in the second session of the webinar, that is understanding the formula car. So as we know, a Formula Imperial is a student formula style hybrid and electric combustion vehicle design and manufacturing event organizing by ISIEINDIA India, and we are starting the event registration for Formula 2022 from today onwards. So and happy Engineers Day to all. And on the occasion of Formula Imperial, and that we are, on the occasion of Engineers Day, we are on, no, we are, sorry for that. On the occasion of Engineers Day, we are launching the Formula Imperial 2022, and we hope that all teams are very enthusiastic to participate in our event. So all the best, and yes, Petlak sir, you can continue with the webinar.
Good afternoon and happy Engineers Day to all you potential engineers out there, and maybe even to me. Okay, what we're talking about today is really a continuation of the program that we started back on Saturday, but obviously there needs to be a little bit of an overlap. So I'm going to step back a little bit and talk a little bit before we get on to car specifics. I'm going to talk a little bit again about the team. I'll bring up some slides so we can have a look. Okay. Now, first thing I'll ask is, can you see that? Can you see that?
Yeah.
You can see that. Good. Okay. I'm talking here about knowledge shortfall. Because of the gap caused by COVID and previous team members having graduated and gone, and there's now a knowledge hole, many teams are effectively starting from scratch. The first thing that these teams must admit is that you don't know anything. Now, I don't mean that in any derogatory way. What I mean is that there are issues and design requirements out there that you don't really understand. And to make matters worse, there are things that you don't even know that you don't know, like why things happen or whatever. I've put a little cartoon down the bottom of the UFO landing, and, the young man looks at it with his mouth open. What the heck's that? The monkey thinks, yeah, I can do that, because he doesn't understand that it's not so easy. He just copies and does what he's got to do. So you're operating in a formula student knowledge vacuum. And as I've said, don't just follow the monkey see, monkey do ethos, where you copy something that somebody else has done. Okay. You're going to look at all the pictures on the internet. You're going to read the advice on Pat's Corner and all the Reddit groups and the internet sites. And they will give you some understanding of what you've got to do, but they won't give you the why answers. And the why questions are the ones that are going to be asked by the judges. The judges, and I Okay, it looks like we're back again. Sharing. Okay, that's our first dropout for the night. We had several on Saturday. Yeah, the judges know what you've done. There really is no new solution in the design or engineering or building of a Formula Student car that we haven't seen somewhere. I mean, I've judged or officiated at more than 50 events over the years, and really there is nothing new. But the questions the judges will ask is why. You know, if you have 10-inch wheels on your car, the judges will ask why, and you have to justify why you've done that. Often they will pose the questions as an opposing point of view. For instance, if you have a car with 10-inch wheels, they may say, why didn't you use 13-inch wheels? And then they will quote some advantages of using the 13-inch wheel. Because what they want to hear is they want to hear you justify the design decisions that you've made. And the knowledge vacuum that I talked about on the last slide means that in many cases you don't know why you made those decisions. You made those decisions just because you copied somebody else or you thought it was a good idea. But it's important to understand these things, to study, to do lots of force diagrams and to work things out so that you can understand why you did it. The judges will accept practical or pragmatic solutions like we're using this particular tire because that's the only tire that we could buy in India, or that's the only engine or electric motor or whatever the case may be. What they won't accept is we did that because we ran out of money or we ran out of time. All those answers tell the judge is that you didn't have good project planning, you didn't have good time management, and realistically, that's probably the most important thing we want to teach you. Okay, you get a team together. Made there, the only person who knows why is you. You have to explain that. Okay, you get the team together, and before you start the design of the team, you need to sit down and have an idea of what you want to do. What do you want to build? Do you want to build an electric car, a space frame car, or what, you know? And I've called this the dreaming part of the project, where you sit down and you have some daydreams, you draw some pictures on paper. Now note, this is not design. You're not designing the car because you can't design the car. You don't have enough information or enough information or enough hard knowledge to be able to start designing anything at this stage. But you've looked at the pictures, you know what you like. You know, I'll guarantee at some stage somebody says, oh, we want to put wings on the car because they look cool. Well, leave the wings for another time. We'll talk about that. We'll talk about that another time. Okay, to start the actual design of the thing, why won't this go on to the next slide? Oh dear. No, it has. Maybe it has. It's locked up, actually. Okay, there we are. We're on the next slide now. Okay, you need a big picture outline, and I've drawn here a sketch of, just a rough sketch of a chassis. And you can see there are two datum points there, the center line of the front axle and the center line of the rear axle, and that's where you start. Now, you cannot determine where those things go until you've determined what wheels and tires you're using, because you need to make sure that the force line from the center of your hub to your differential center or the suspension at the front is at right angles to the center line of the car as close as possible. So to find the height of the hub, where you're going to put your differential, where you're going to put your engine, where you're going to put your steering gear and so on, you actually need those wheel heights to start with. Okay. Also at this stage, you have some issues with rules. You know, you're going to have to fit into this car. You're going to have to fit the templates. The templates I include Percy, the mannequin. He's got to fit, and he's got to fit according to the rules. Then you need the cockpit opening template, which has to pass down through the top, and you need the footwell template, which has to pass through into the footwell. And then you have some other rules, side impact structures, and all those sort of things that you have to accommodate. It's probably a good idea at this stage to make a very simple wooden mock-up of the car to sit on the floor, so that you can find the ergonomic solution for the drivers. You know, you don't want the drivers too cramped. You don't want the steering wheel too far away. You know, you don't want the driver's arms hitting the side of the chassis when he tries to turn the wheel. All of those sort of things. The drivers get very tired very quickly, so you need to make sure that they're comfortable. And we'll come back to that. Okay. Now, that brings me to the first of Pat's rules. I have a lot of rules. They're Pat's rules of 3. And this is the first one. And I want you to actually write this down somewhere where it's not going to get lost. If in your design area you have a whiteboard, I would ask you to write this in the top corner of the whiteboard, but not in a erasable pen. Do it in a permanent pen. And I'm telling you that all things being equal, same tires, same driver, same engine, etc., the car with the least weight will win. F equals MA has not been repealed. The car with the lightest weight will win. With your F equals MA, your F is limited by the grip that you can generate by the tires. The M is the mass, and A, of course, is acceleration. If you want to improve the acceleration in all aspects, lateral acceleration and longitudinal acceleration, you need to either increase the F, which is almost impossible or very expensive to buy, very expensive soft race tires, or to decrease the mass. Now, how do you decrease the mass? Very simple. Don't put it in the first place. If the weight is in there, it's impossible then to remove, because it's actually doing something. This also relates to your design at this stage, because if you can design a bracket that does 2 or 3 jobs or 4 jobs all in one little bracket, then that saves the weight of having 4 brackets. It also should dictate some design decisions about what bits you need on the car. I have another rule of 3, that rule being that anything that's not on the car doesn't cost anything, it doesn't weigh anything, and it cannot break. So if it doesn't need to be there, it doesn't need to be there. And I include, for an inexperienced team, wings don't need to be there. Push rods and dampers and all those monkey motion suspension things that people are so fond of, they don't need to be there. So by eliminating all of those things, you can decrease the number of nodes and load points you need in the chassis, and therefore simplify the chassis. And that comes way before you start trying to incorporate engines or whatever. Okay. So it's not kind of warning. Yes. Okay. The choices that you have to make is, firstly, which event are you going to attend? Well, obviously, at this point in time, we're talking about Formula Imperial at Noida. But there are other events in India which you may wish to attend. There's Supra, there's Bharat, there's several events. There are also some overseas events you may wish to attend. Each year in Germany or the UK, we often see Indian teams attend. But you need to make those decisions before you start designing, because unfortunately, the rules for some of those events are a little different. Okay, so are you going to build a combustion car or an electric car? Is it going to be a space frame or a monochrome chassis? What tires are you going to use? What engine or electric motor are you going to use? Tell me about your brakes. Tell me about your driveline and your suspension. There are more, but these are the big ones. So I'll talk about these things one at a time and make suggestions about what I think you should be doing. So if you follow these recommendations, your first car won't be a goat. I don't mean a billy goat, a useless. What happens there? Yeah, I don't mean a useless thing, but it's not going to be hopeless. It's going to be a reasonable effective car that you can drive through the event, you can finish the event. But it's not going to be a GOAT, the greatest of all time either. And you must accept that. You must set your realizations that you cannot build an A car until you have an A team. And an A team, I mean, is a team with experience, knowledge, abilities, funding, the other things that you need. So you have to be realistic that when you're going to the event, an inexperienced or a new team are not going to win it. Another rule of three, in motorsport, you have a choice of three things. You can either be fast, reliable, or inexpensive. But you can only have two of those. If you want to be fast and reliable, the car is not going to be inexpensive. If you want to be inexpensive and reliable, the car is not going to be fast, and so on. So from those three things, you need to choose which is the most important. Now, normally you jump in and say, oh, fast, we want to build a fast car. But the truth of the matter is you don't know how to build a fast car, and you certainly aren't going to build a fast car on the limited budget that every new team has. Remember, it's not going. If it's fast and cheap, it's not going to be reliable. So you need to determine which of those 3 points or which of those 2 points are the most important to you. If you haven't got any money or you haven't got much money, and that's most teams, that decision is already made for you. Okay, so it must be inexpensive. So your second choice is, now, do I want it to be fast or do I want it to be reliable? Well, no team ever said, oh, what we want to do is we want to go to Formula Imperial and we want to do 3 laps, and at the end of 3 laps our chassis is broken and we sit on the side of the track and we watch everybody else having fun. It's far better to go there and drive around and finish the event, maybe in 15th place or 20th place or something like that. That really doesn't matter. But you finish the event, you've achieved what you set out to achieve, you have, you join the after party, you're part of the successful teams that have actually succeeded in learning from Formula Imperial. So, sadly, the one that must be sacrificed is fast. You need to build a car that's reliable and inexpensive. Okay. Now, combustion or electric? I've shown the guy making the choice. He's stepping over the fence. It's a big choice. I would never recommend for a new team to build an electric car. Now, I understand there are reasons why you'd want to do that. Not the least being that your university might insist. But although it's a nice idea to think about, saving the planet and reducing emissions and all those things, they can all come later, because right at the moment, what's the intent of Formula Imperial is to finish off your education. The universities, unfortunately, don't give you any sort of practical course to enable you to use the lessons that you learned in a practical way, whereas Formula does that, and it does that in an exciting and interesting way. If you choose to build an electric car, you have to understand that it is a much more difficult task. It's also a more dangerous task. So if you have any choice in the matter at all for a first car or an inexperienced car, do like the majority of the other teams in India do, and go find yourself a wrecked KTM 390 and use the little single cell. Okay. As I've said, for an experienced team, only one answer. One comment I will make about electric cars, and that is that You have to be very well aware that the high-density batteries, the lithium LiPo, lithium-ion, lithium polymer batteries that are used can be extremely dangerous. Firstly, their power density is very high, so the voltage is quite high. You can get quite a nasty shock. Also, they tend to catch fire if they're abused. And when they catch fire, two things happen. Firstly, fatally toxic. We've seen several cars, couple of university workshops, and in fact a hotel in Germany actually burnt down when a Formula student battery caught fire and couldn't be extinguished. When we went to check the reasons why, we found that invariably the cause was abuse, either in the assembly of the accumulator, or in several cases it was swarf, metal filings or shavings in the battery box, which punctured one or more of the little pouches, and fire happened. So if you choose to go down the electrical route, you definitely need to get some training relating to electric vehicles, the handling of electric, the accumulators and batteries and whatever. Even in Formula One, when they went to the hybrid Formula One cars, I recall in the first year, one of the BMW Formula One cars, now Sauber, or now Alfa Romeo, one of them pulled into the pits, and a mechanic walked over and touched the car and was immediately thrown 10 feet backwards from a massive electric shock that he just got from just touching the car, because the carbon fiber monocoque of the car was conductive and there was a short somewhere in the system. So even at that Formula One level, where you think they're supposed to know everything, even there were accidents happening. Okay. What type of chassis? Well, I said here that, again, for a new team, there really is only one answer, and that's a multi-tubular space frame. The business of constructing a carbon fiber composite car or a honeycomb aluminium monocoque car is really, really quite difficult. But the worst thing goes back to the business of you don't know anything. When you get part of the way into the construction and you realize that you've actually made a mistake, or no, not made a mistake, but you actually made a decision based on false information or false knowledge. With a monocoque car, there's very little you can do to correct it, apart from throw the thing away and build another one. With a space frame car, a steel space frame car, you can take the hacksaw and some tubes, cut those tubes out and do what you've got to do, and then repair or modify the chassis if needs be, without losing any of its integrity. There are some issues with universities where some universities will insist that the team build a monocoque car, especially a composite car, because they want the students to gain experience in handling or working with composite structures, because I guess composite structures are a part of the future. But it's very difficult, and it's certainly very difficult if the university doesn't give you the facilities and the training and the budget that you needed to do that. But yet there are other universities who insist that the team build a space frame car. Why? Because the professors look and they know that in a space frame car, it is very easy for the students to see and understand the load paths. Like when you feed a force into the chassis, where does it go? Where do you react it? How does it, how do you dissipate that into the chassis? And it's much easier to see with a tubular structure. And it avoids you doing things like, putting a heavily loaded node, or not a node, but a heavily loaded point say, in the middle of an unsupported tube that's going to flex and bend and break, you know that that's got to be supported. You have to make a note. Okay, we'll move along to the next slide and see what happens. Okay, next thing we were going to talk about was tires. Now, most people at this stage would recommend that the team join the TTC, that's the tire testing consortium, and make their choice based on the data from that site. Trouble is, at your level of knowledge, you've got no idea what the data means or what to do with it. That knowledge is not of any value to you at this stage. So my recommendation is to choose a 13-inch tire from one of the several suppliers of Formula Student tires, if possible, or a race tire of some description, preferably, and then make that choice work. In the real world of motorsport, they don't use tire data to choose tires. Again, if you look at Formula One, in Formula One, you put on whatever Pirelli supply for that particular race. You have your choice of the red, the yellow, and the white tire, and you then choose which of those tires you use, and away you go. There's no thinking, oh well, if they had a purple tire with green stripes on it, that'd be better. You don't have that choice. You have to use what you've done. So what they do is they fit the tires, they test, they log their data, and they learn how to make that tire work. And that's exactly what you should be doing. Worry about tire test data for next year or the year after or sometime. Now, of course, the why question will be asked by the judges. Why did you choose that tire? Now, time for a pragmatic answer. You tell them that, of course, in India, the market is a bit limited. Or the choices. Okay. So, engine choice. I've already recommended that you use a combustion engine. So then what engine do you choose? Question, what engine's best? Answer, whatever you can get your hands on. The only thing I would say there is be careful with air-cooled engines. There are lots of air-cooled Royal Enfields in India. If you choose a Royal Enfield engine, and many teams have in the past, and there's no reason why you shouldn't if you choose to, apart from them being a bit heavy, but you definitely need to get airflow to keep that engine cool. Tucking the engine in behind the firewall behind the driver means there's not going to be good airflow to that engine, and it will overheat. The KTM engine and the BMW engine, the other little engines which are available there, they are all water cooled. So that's a better solution, because you can have a radiator mounted, somewhere on the side of the car or whatever, and you can get that engine cooled. Looking at data from teams, you know that cars in Formula Student competition spend less than 15% of their time at full throttle. So people think, oh, power is critical. Well, power is not that important at all. Only 15% of the time you're running at full throttle. So what's more important is drivability, especially for inexperienced drivers. You don't want a car with a snatchy, peaky power delivery, one where the driver puts his foot down and nothing happens for 2 seconds and then it jumps off like a scolded cat. You want a car that's nice and progressive, nice and easy to drive. And that's more important than having 100 horsepower. That's much more important. Okay. The rules will require that you fit a 19 or a 20 millimeter restrictor in there. And that's how we basically handicap all of the engines that you might use. Remember, you can use an engine of 710 cc's in this event. The 19 millimeter restrictor goes with ethanol fuel, and the 20 millimeter restrictor is used with gasoline, petroleum fuel. And this can cause some tuning issues. Now, on the little monocylinder engines, the single-cylinder engines like the KTM, if you use the standard throttle body with the restrictor, this causes huge problems. These engines have typically a large diameter throttle body, more than 40 millimeters. I think the KTM might be 43 millimeters, and some of the others are 46 millimeters. So when you go to open the throttle, you only have the throttle open about 1/3 of the way when there is enough airflow through the throttle to saturate the restrictor. That's all the restrictor can flow. So what happens then if you open the throttle more? You're not getting any more air into the engine. However, the throttle position switch is telling the ECU that you are putting more air into the engine, and it will try to adjust the ignition timing and the mixture to suit the extra airflow. And all that happens is it drowns the engine, and I've actually seen a KTM seized because of this, but certainly I've seen them where they just won't drive. The classic symptom is the driver says, oh, the car goes better when I lift off the throttle. So I try to accelerate full throttle and the car is jumping and bucking and making noises and won't go. But if I close the throttle a little bit, oh, it takes off. That's because the airflow is more closely matching the restrictor. In this case, I've shown a photograph of a restrictor. You can see the size of the throttle body and the size of the small hole in the restrictor, and you can see exactly what I'm talking about. The answer is to use the restrictor, a smaller restrictor, and adapt it from another vehicle. Some companies make special restrictors for Formula Student cars in the right size. Sorry, not restrictors, throttle bodies. But more easily, to find the throttle body from one of the 150cc fuel-injected bikes that are around in India. Or even a Tata Nano. I think Tata Nano's got a 28 millimeter restrictor. The size you want is about 23 to about 28 or maybe 30 millimeters maximum, but no more than that. Any more than that and you're going to run into the problems. Same thing as you need to relocate the throttle position, use the throttle position sensor from the smaller throttle body, and you will need to remap the ECU. Whether this is to use an aftermarket ECU or whether it is to use a little piggyback, a piggyback ECU that effectively tells lies to the main ECU, or whether it's you've found somebody who can remap the original KTM ECU. That's a problem that you have to do. But it's one of the difficulties. You know, the little KTM engine is very attractive, but not quite so easy, especially getting the fueling right. Okay, intake restrictor. I've talked about, make a restrictor. The picture we saw was just a flat plate under the throttle body. Well, you can do much better than that. You can have a converging, diverging cone, the restrictor in the middle, and you can recover quite a lot of the lost pressure. Okay. Talking about the exhaust silencer, the Formula Student rules set a maximum exhaust noise level. They're covered in either the Formula Student rules or in the supplementary regulations for the event that you're running in, like Formula Imperial. If you exceed this noise, you'll not be permitted to compete in the dynamic events. And that's a really dumb way to get disqualified. We've had teams argue that they're using the standard exhaust system and muffler that came on the motorcycle, and they find that it won't pass the noise test, and they don't understand this. Well, unfortunately, that's the case. You need to ensure that your muffler passes the exhaust test at the event. So you need a good sound meter. Need to do some testing with some advice from people who understand about such things. You need to keep away from reflective walls and noisy backgrounds and various things. And you need to tune your exhaust or tune your muffler to give you a couple of decibels of credit to ensure that you don't run into problems when you get to the event. What happens at the event, we see it every year, is the teams fail the noise test and then they take the car away and they start to jam things down inside the muffler to try to shut it up. All that does is reduces the flow of the exhaust system and increases the back pressure. And the end result is that the car runs dreadful. It doesn't drive well. It doesn't go well. It completely ruins your event. So that's a really dumb way to get yourself disqualified, is with the noisy. Okay, the final drive of a Formula Student car is that it usually consists of a chain and a drive to a differential and then to the wheels via articulated axles. Sometimes, of course, that differential is not a differential at all. It's a spool. Okay, most cars, I guess, are fitted with a differential to balance the rear wheel speeds. Usually this is a limited slip differential of some kind, but there are other options. Now, a limited slip differential is a differential that instead of a standard differential, if a wheel loses traction, if you pick a wheel up in the air or it hits a puddle or something, all the torque will go to the wheel with the least grip. A limited slip differential will limit that amount of slip and send some percentage to the wheel with the most grip. So that's much more of a suitable situation where you're trying to go fast. But it's not the only solution. Here's a spool. Now, a spool is simply a solid connection between the two axles. In this case, if you have a look, it's got the drive sprocket on the left-hand side as you look at it, and the brake disc, rear brake disc on the right-hand side. And it's got the universal joints and the axles out to the chassis. Now, immediately the question is, how the heck does that work? Because when you go around a corner, the outside wheels have to go farther than the inside wheels, so the car is not going to want to turn. It's going to understeer, it's going to push, it's going to be slow. And the answer is that yes, that's actually 100% true, unless you understand what you're trying to achieve and you tune your way around it. And there are ways of doing this. As I said, go-karts manage to corner at speed without whilst being fitted with a rear axle, solid rear axle. So how do they do it? How do they achieve that? So if you have a look at this picture, the little yellow arrow shows that it's actually carried an inside rear wheel, and that allows the difference in speeds between those two back wheels. Remember, it's the outside loaded wheel that's actually doing the work. So how did you get the car to actually pick its inside rear wheel up? Well, the next picture shows, if you have a look at the two red lines, you'll see that the red line across the top of the rear tires is not parallel with the red line across the top of the front tires. Something is twisted to allow that wheel to come off the ground on the inside. Now, I've had innumerable people tell me, oh yeah, go-karts have flexible chassis and whatever. Well, let me tell you, it's got nothing to do with flexing the chassis. This is all to do with using the steering geometry at the front of the car to introduce a diagonal weight jacking in the car, so that when a lateral force is applied with some steering lock on the car,
Dear teams, please be in the meeting. There is some technical problem at the stars end.
Back again. You can see me. See my slides. Okay, back to where we were. If you have a look at this picture here of the car chassis with some steering lock, you can see that the inside wheel, the geometry, the kingpin inclination or steering axis inclination, and the caster and the scrub radius has actually forced that wheel down. The lateral forces operate from left to right across the chassis, and that puts three wheels back on the ground and floats the inside rear wheel. Now, as I said, you don't necessarily need to actually get the inside rear wheel off the ground, because if you reduce the load on the wheel, you change the slip angles between the two rear wheels, and now you actually have shall we say, a differential in the slip angles. And some of the very fastest cars in Formula Student use a spool. The car that I showed you before, this one here, this is the Monash car from Melbourne in Australia. And at the time I did this picture's from 2015. This was the number one Formula Student team in the world. They'd won events in the UK, in Europe, in Australia, of course. Very, very successful. We're back again. Okay. What I'm saying is that if you use a spool, you reduce the mass in the back of the car, you reduce the rotational inertia, reduce the cost and complexity of a differential. It's very easy to use a single rear brake for both rear wheels. And this has some additional benefits in that the brake will have to be a little bit bigger, as will the caliper. And in fact, you can then use the same brake and caliper as you're using on the front of the car, which reduces your spares, the logistics of your spares, what size brakes and calipers and stuff you're using. Now, if you choose to use a spool, and I don't see any reason why you shouldn't, you must get the car finished at least a month before the event, because you are going to have to test. Firstly, the car is going to need to be set up. That is, that the car will need to be adjusted, the front and rear toe and camber angles, the weight distribution, maybe the position of the driver in the seat, the amount of Ackerman or non-Ackerman that you might be using. And secondly, it's important to teach the drivers how to drive it, because a car with a spool must be driven more aggressively than a car without a spool. So if you have a soft driver, he's not going to be able to make the most of it. He actually has to be prepared to chuck it into corners a little bit too, and not be afraid to use the throttle to steer the car as well as the steering wheel. And that only comes from practice. So that's something you got to do. Okay, back to where we were. Yeah, we talked about that. Important, if possible, to ensure that the brake shafts or the drive shafts are approximately the same length, or at least have the same torsion capacity. So if you have a little short drive shaft and a big long drive shaft, the car is going to do what we call torque steer. When you accelerate hard, it's going to wind up the long drive shaft, but it won't wind up the stiffer short drive shaft, and that will cause the car not to run in a straight line. I saw a German car crashed in the UK exactly because of this in the acceleration event in the wet. The driver accelerated hard down the acceleration, not knowing that he was winding up the long axle. The car was drifting, but he was correcting the drift with the steering wheel. When he reached the end of the acceleration event, he closed the throttle. Immediately, the torque that was stored in the long axle unwound itself and steered the car straight into the wall. Bang, smashed the whole front end off the car, and that was the end of their event. Needless to say, the team were very upset. In this case, you can see that this is the Stuttgart team from 2014, and you can see that the differential is off to the left-hand side of the car, where that ring of bolts are. That's a German Drexler differential. But they've actually made an extension to extend it to the right-hand side to ensure that both the drive shafts are actually the same length for that reason. If you look under many ordinary little front-wheel drive touring cars, you'll see they've done something very similar. Okay, suspension. Now, as I said, there's been more BS written and more time wasted on suspension geometry than on any other aspect of Formula Student design. I talked on Saturday about druids and all sorts of black magic stuff. Well, unfortunately, it's still around, but we'll try to get rid of some more of it. Okay. The Formula Student rules require only 50 millimeters of suspension travel. Don't use any more. Remember what Colin Chapman said. Colin Chapman, the famous Lotus designer, no longer with us these days, but he said any suspension will work if you don't let it. Now, he's not talking about building go-karts with no suspension. What he's talking about here is limiting the suspension travel to the absolute maximum amount that you need. The rules require that you have 50 millimeters of travel, 25 millimeters in bump and 25 millimeters in droop, and you don't need any more than that. So then you have to ask yourself, how much camber change can be generated in 50 millimeters of travel with a standard Formula Student type suspension design? And the answer is very little. Okay, so you'll find that the tire will operate in a range of cambers, say from 0 camber to -4. So if you can keep the tire in that window over its whole operation within the car, your suspension geometry is not important. As long as you can keep the tire in that operating window, it will perform acceptably well. I said here, but unless there is excessive compliance. Now, compliance or flexing or whatever in the structure can give you more camber than you thought you had. If we assume that the chassis has adequate torsional stiffness, and I've actually given you a number there, I've said 1500 Newton meters per degree is plenty. Cars will be much higher than that, but 1500 Newton meters per degree is okay. The rule of thumb is that your chassis stiffness should be 1 order of magnitude greater than your suspension roll stiffness. Okay, so to achieve this, the designer must concentrate on feeding all of the wheel loads into the chassis with a minimum amount of compliance in the parts and assembly. So you need to feed the loads into the chassis at a node, like the apex of a triangle. You need to feed it into brackets that are significantly strong enough or stiff enough. No, strong is not the right word. Stiff enough to resist any deflection, in order to ensure that the wheels and suspension are actually doing what the designer intended them to do. Question: who can tell me the greatest force that the chassis must react? What's the biggest force that you can feed into the chassis? Anyone want to pop up on air and put a number on it? Okay, don't worry. It's the brake torque that's generated around the front spindle, the front axle, in a maximum effort stop. Okay? And most of this is concentrated in the front lower control arm. If you do yourself a force diagram, you can actually see that. You take into account the brake torque and how the vehicle inertia and all those things. You'll be able to see that the lower control arm is the one that does the majority of work. And if you don't get it right, that's what's likely to happen. That's a car which has had a double lower A-arm failure in the brake test. It's in the brake test and crash. At least they made the same mistake on both sides, but that's extremely embarrassing. They get to the brake test, the car brakes, and that's the end of their event. Another reason why you need to test, and you need to test brake tests and noise tests and all the other things. I see the guy in the background running over to try help, but it's all too late. As I said, the front control arm should be a broad-based triangular structure pivoted on the chassis at appropriate nodes. The team should avoid using threaded rod ends anywhere on the lower front wishbone. Rod ends or threaded clevises anywhere loaded in bending is that's a design failure that the judges will not forgive. Okay. Your suspension design should arrange that the lower wishbone is parallel to the ground in the normal ride height position. So in your 25 mil up, 25 mil down, you get in the middle. Your lower wishbones, front and back, should be parallel to the ground and as long as practical. Now, the reason for this is so that when the suspension operates, we're back again. Okay. I'm talking here about generating lateral scrub at the contact patch of the tire, which is something you don't want to do. The trick, I don't like using that word, but the trick to good road holding is to keep the tire happy. Do not excite the tire at the contact patch. That's where breakaway occurs and you lose grip. Okay, I've also said that the longitudinal axis of the wishbone pivot should also be parallel to the ground. That means that we're not going to have any anti-dive or anti-squat in the chassis. That's a rabbit hole that you can go down and get completely lost in. And it is, many suspensions are broken because the designer has included anti-dive or anti-squat. The result of this geometry takes the suspension compliance away from the springs and puts it into the suspension arm, so it binds up the four bar linkage and can cause failures. Don't do it. Now, here's a photograph I took, and you can see the amount of front camber, positive camber, that's been generated on this car. Is it the front or the rear? No, the rear. It's rear camber that's been generated on that car in a corner. This picture was taken in Germany. The car handled very badly. It was oversteery and it didn't respond properly to the driver's input. When I showed this picture to the designer of the car, he said impossible, can't happen. I said, well, the picture shows it does. He said, oh, it must be something to do with the shutter in the camera. I said, no, you're generating, and the tire temperature showed that his tires were overheating on the outside edge. So definitely was an issue in the car. He displayed the geometry of his suspension, and sure enough, it was physically impossible for the suspension as designed to actually go into positive camber like that. So how the hell did it get there? Well, it got there from compliance, but the compliance was actually in the wheel. It was the wheel that was flexing. So by the time the next event came around, the team had new wheels. They had designed their own wheels and made their own wheel centers, and hadn't taken into account that the wheel center itself was actually flexing. And they're very lucky that they didn't have a wheel failure, because we've had many wheel failures caused by that very problem. All right. Whoops, what's happening here? Okay. While we're on the subject of tow, what tow settings should you start with? Just as a rough rule of thumb. I did mention this on Saturday, but I'll say it again. Before you go out, first time out, you should set the front tow to about 3 millimeters of static tow out. Tow out on the front. There are reasons for this. I know that most road cars are set with tow in, but on these little race cars, you need to tow out the front wheels a little bit, about 3 millimeters. And at the rear of the car, you should set the tow in to about 3 millimeters, and that's tow in. Now, the reason why you set a tow out to the front is to generate a better bite and a better turn in, because in Formula student events, you're forever trying to negotiate your way through slaloms and around witches' hats and God knows what. But at the rear of the car, you need some tow in to settle the car down, because you don't want the car breaking away or becoming tail happy, especially when the driver has the brakes on. He wants it to be stable under brakes. As I said, these are a starting point, and they should be optimized or adjusted by measuring the tire temperatures. I'm talking there about the tire. The team needs a proper tire pyrometer, not an infrared gun. An infrared gun only measures the temperature at the surface of the tire, whereas you really want to measure the temperature in the tire tread itself. Now, you can buy a needle-type pyrometer adapter for most multimeters. They're quite cheap. They convert the degrees Celsius to millivolts, and you read millivolts on the multimeter. Generally, you should be looking for tire temperatures hot around the 75 or 80 degree mark. The outside edge should be a touch lower than the middle, and the inside edge a touch higher than the middle. So if you have 80 degrees in the middle, you might want 85 on the inside edge and 75 on the outside edge. But that's not a real number. That's a guide. Okay. I said here, the chassis must accept all 3 templates plus the tallest driver. Remember this, that your car might pass with Percy, but if your tallest driver is taller than Percy, he may not be allowed to drive the car in competition if he fails at technical inspection. So for the sake of a millimeter or two, just err on the conservative side. Okay. When the driver sits in the car, he must be comfortable and well supported. Some cars are absolutely horrible to sit in. You can't really drive them. The car should be more comfortable to sit in than the car that you drive on the street. It should be possible to just go asleep in there, comfortable. And I've said here, just think about the support given by a child safety seat. So have a look at the safety seats that people put babies in, strapped in the back of a car, and look how they're designed to carry the child in such a way that the G-forces or whatever don't damage or hurt the child. Good place to copy. Okay. A very common error made by beginning teams is to design the chassis first. This is a classic error. The chassis is simply a very complicated bracket that holds everything together. Now, until you know what you want to hold together, you can't design the bracket to do so. What happens is that you end up adding on bits and welding in tubes and more brackets and more tubes and more, and your chassis ends up being heavy and ugly, complicated, and generally looks very unprofessional. Do this by design your chassis by populating your CAD program with a constellation of points that you need. So all the things you got to put in the car, the pedals, the steering wheel, the templates, the engine, the side impact structures, the main roll hoop, the secondary roll hoop, all those other things. So you populate the thing and then realistically just join the dots. And you join the dots in the most sensible way. If you find in the chassis that you've got some load points only a few millimeters apart, then try converge them into a single load point. So you might, for instance, have an upper suspension link and a coil spring shock absorber mount and an anti-roll bar and the steering box all mounted on the same node, rather than 4 separate nodes to do the job. So that takes material out of the chassis, or material you don't put in the first place, makes for a very sanitary design, very good way to do it. So the design of the chassis actually comes relatively late in the project. You don't go build the chassis first and then start attaching things to it. That's a beginner's mistake. Okay, so time to get started. So I want you to build a simple space frame car, 13-inch wheels, design a simple suspension system, no belt cranks and push rods and all that nonsense. Choose an engine, choose a differential, freeze your design, and now keep it simple and build the car. Get going. You should be well on the way to building this car long before the event. You need timekeeping and time management is so important because you must get it finished. You must get it driving at least a month before the event because you must test. Because I promise you, it's going to break. It is going to break, and you need to find out why it's going to break. You fix it and make sure it doesn't break again. There's nothing worse than take the car to the event, like our friend in the brake test we saw a few minutes ago, and the first time he stands on the brakes, the front suspension collapses, and that's the end of their event. You don't want that to happen to you. Okay, so we're down to Pat's Formula Student Simple Suspension Design. I told you that, this field is littered with old druids and magicians that talk about all sorts of black magic. Well, I'm not one of those, and so I'm going to give you some advice so that you keep it simple, straightforward, and you build a car which will be easy to set up, easy to drive, will work pretty well, make its tires work pretty well. Okay, so first we're going to talk about from the front of the car. So first you start with the wheel and tire. I told you that back at the beginning of this presentation. You need the wheel to determine what your axle height is, what the axle height is, also the clearance of the car. Remember that you need, the rules of the competition mean that you cannot ground the car. The car can't run out of travel and ground on the road. If it does that, you'll get black flagged. So if we have 50 millimeters of suspension bump, plus maybe a little bit of compliance, I think I'd be wanting to have about 75 millimeters of travel. But that goes, ground clearance. But that goes against one of Pat's rules. Remember I said that the car with the lowest center of gravity will win. Well, obviously you want to keep that road clearance as low as possible without having it hit the road. Okay. Teams will argue that, the 10-inch wheel has lower rotational inertia and various other things. But believe me, it's also much more difficult to incorporate because there is less real estate, less room inside the wheel to incorporate your brakes and suspension and steering, all the things you got to tuck in there. And for a beginning team, it gets very, very difficult. Also, you must remember that the loads, especially that big braking load that you're reacting through the suspension upright in here, obviously the wider the base over which you can react those forces, the better the load path is into the car. And I've said here that most of the low inertia benefits of a 10-inch tire can be recovered if you use the Continental low-profile radial tire. The Continental Tire Company make a low-profile radial Formula Student tire. I honestly don't know if you can buy it in India, but I have seen the tire in India. So either Continental do have it there, or teams have been able to import it from Europe. Okay. The wheel on the car will run at negative camber, so I've just drawn it here at a nominal 1 degree. This is just to illustrate the center of the contact patch. Now, the center of the contact patch is not in the middle of the tire. As we tilt the tire over towards the car, the center of pressure actually moves inboard a little bit. And the reason I've drawn it that way is because that's where the forces are applied. Many times you'll see drawings which will show you scrub radius measured to the center of the tire. Well, it shouldn't be measured to the center of the tire. It should be measured to where the load is applied, and the load is applied at the center of pressure. A small amount of scrub radius is a good idea, mainly to give the driver some work to do. If the steering is too light, if the steering has no feel, the driver can't feel the tire work, and it makes it difficult for him to drive accurately to impart the correct amount of steering lock or opposite lock that he needs to do to control the car, especially when he starts going a bit fast. About 50 millimeters is a good number, good place to start. Okay. A Formula Student car doesn't need much steering axis inclination. And steering axis can actually have a negative effect because it does tend to fight against the weight jacking that you want to make a spool work. So I've said here that a good compromise for manufacture is to have the steering axis equal the camber, as this eases the manufacture of the upright. And what I mean there is that means that the axle line is at right angles to a line drawn between the top and bottom ball joint on the upright. So it makes it easier to jig up and to manufacture when you're actually making these things, rather than have some peculiar angles. In this case, you can see the scrub radius here in the drawing. Down the left-hand side, the scrub radius is the distance at the ground patch between where the line drawn through the top and bottom ball joints on the upright intersects the ground and the center of pressure of the tire. Many times I've seen this would be shown over here somewhere in the middle of the tire, which gives an excessively large idea of what the scrub radius should be. Okay, the lower control arm should be drawn in. We talked about this before. It should be parallel to the ground and as long as possible. This is to reduce the lateral scrub at the contact patch. Look, we have some scrub, but we don't want it increasing and decreasing as the suspension works. Okay, the front virtual swing axle length. In other words, when we draw a line out from along the bottom wishbone and the top wishbone till they intersect and bring it back to the contact patch, from the intersecting point out here somewhere back to the ground should be about 2.5 times the track width. So if you have 120 millimeters of track width, you should have something like close to 300 centimeters of virtual swing axle length. Now that will change. The instant the suspension moves upwards, that VSA will get shorter, and the instant the wheel moves downwards, that VSA will get longer. So it's not very important. With this design, it will automatically, I'll go back. With this design, it will automatically happen that when you draw a line from the contact patch out to the instant center, it's going to cross the center of the car over here somewhere, about where the arrow is, and that's where the supposed roll center will be. Yeah. Excuse me. In real terms, when the car is operating on the track, the roll center is not there at all. It moves around all over the place. So I'm not even bothered about it. It's just, it's a good point to remember when we start that our roll center should be, I don't know, 3 or 4 inches above the ground at the front and on the center line of the car. But really, to me, it doesn't matter. Okay. I said, remember, there's a third lateral link at the front, and that's the steering rod. So the steering system must also articulate through the same angles as the suspension geometry. Otherwise, you'll get bump steer or roll steer. That's to say, as the vehicle rolls or as the wheel travels, the wheel will steer in and out, and that's not something we want. So if you try to keep the pivots in line, that will reduce the amount of bump steer at the design stage. And then you can tune the bump steer out once the car is finished by maybe raising or lowering slightly the position of the steering rack in the car. Okay. Looking, steering and suspension top view. So we're now looking down from the top. The purple wishbone is the top one, the shorter one. The green one is the bottom control arm, and the blue one is the steering link. And I've drawn in the Ackermann angle as being 100% Ackermann in this case. 100% Ackermann means that this line drawn from the steering axis through along the center line of the steering arm and continue out will intersect in the middle of the rear axle. Is it important? Not in the least. The reason it's not important is that you can adjust the Ackermann angle itself is not important. What we're actually after is to have the tires develop the maximum slip angle that you require as you steer the car, regardless of the amount of steer that you've got. These wheels do not run around the track like a train on rails. There are slip angles involved. And you can determine whether you've got a tire which is being dragged sideways down the track or being pushed sideways down the track by measuring the tire temperatures. That will also show you whether you have sufficient Ackermann or insufficient Ackermann. But you can fine tune it by small changes to the actual static toe. So if you need a little more Ackermann effect, maybe toe the wheel out another 1 millimeter. It doesn't really matter. Toe the wheel in 1 millimeter. Okay. So I've actually made a note on there saying that the actual steering position in the car will be set by the need to pass the footwell template. The footwell template is an absolute hindrance when you're trying to get proper steering geometry, especially if you want to have the steering rack behind the axle line, which where most Formula Student cars have it. Okay, so at the rear of the car, again, for a new team, I recommend a 13-inch wheel for reasons that become clear. And I've said the same as the front, the low inertia can be recovered by using the Continental low-profile tire. Okay, at the rear of the tire, again, I've drawn it with 1 degree of camber and to find the center of the contact patch. Now, at the rear, I want to have the scrub axis at 0 or as close to 0 as possible. Why? I want to reduce the steer moment on the rear axle because rear steer compliance is probably the worst design mistake that you can make in a Formula Student car. It will make the car almost undrivable. It's hilarious to watch a car with compliant rear steer on the skid pan as the driver just takes bite after bite after bite, trying to get the car to steer. He turns in, the load comes on the back axle, the wheel turns in or turns out, the car steers from the back, the driver corrects from the front, that changes the back, it goes back and forth, and the end result is that it's just slow and he knocks cones over. So try to keep the rear scrub radius at 0. Okay. At the back, I'm suggesting you use a rear virtual swing axle length of about 2 track widths. Remember at the front I said 2.5 track widths. And part of the reason why I can use it longer at the front is that I gain some camber from the caster effect on the loaded wheel as I turn into the corner. So I don't actually need the swing axle length to give me the camber that I need to generate the maximum tire grip. But I do at the back. Then I said the desired camber gain, in other words, the amount of camber change as the wheel goes up and down, can be achieved by adjusting the length of the top link or the position of the top link, but the length of the top link is the easiest one. Okay, rear suspension link should end up looking something like that. You can then design the upright or a previously upright made used with whatever compromises needed reduced to a minimum. So if you're using something from last year, well, you know what you've got to try to do to use it to the best advantage. Now, rear suspension top view, I've shown the bottom link, that the bottom suspension arm as a what's called a Z arm or a Z arm. The distance between the 2 points out here is called the toe base, and you need to keep those well wide apart in order to give sufficient stiffness to prevent rear toe compliance at the back of the car. Another reason why a 13-inch wheel is a better choice than a 10-inch wheel, because it gives you a little bit more room to do what you've got to do in here. There was a question the other day, or a question on Saturday, where somebody suggested that a direct acting suspension on the back of the car is difficult because of the difficulty in positioning the coil spring damper unit. But if you have a look at this type arrangement, I would probably connect the coil spring damper unit from this point out here up to this point here on the chassis, or very close to it. That moves the coil spring damper away from the axle, which was the problem that the designer was complaining about. So no need here to have belt cranks and all those other things that you don't need. Okay, moving along, rear suspension side view. You'll notice that the pivots are parallel to the center line of the car. There is no anti-dive or anti-squat in this car. Now, like at the front of the car, we had a third member in the front of the car, the steering link. At the back, we've got a third member, which is the axle. And it's almost impossible that you're going to make the axle geometry compliant with the suspension geometry, because the axle is going to be much longer and it's going to pivot between these 2 points, which is much longer. So we need to be able to accept some change in length of the axle as the suspension works. Otherwise, it will bind up the suspension, maybe break something. The best way around this is to use a tripod universal joint at the inside end. These are common as anything. And on the front of almost every little front-wheel drive car known to man. They are not difficult to find at all. Find and adapt. Some teams will make them. They accept a significant plunge whilst they're articulating. They are a constant velocity joint, so they're not changing the angular acceleration as the shaft rotates like an ordinary universal joint or a hook joint would do. Very nice and tidy solution, and as I said, used on virtually every small car made. They're certainly used on Tatas and Maruti Suzuki's, all the other little cars that you've got in Hyundais and Kias and Fords and Volkswagens, all the other little cars that you have in India. Okay, now chassis visualization. I've drawn this up as just like a visualization, a dream of what the car or what a chassis should look like, what the car should look like. So as few tubes as possible, nodes. This case it's an electric car. It's got electric motor and transmission in the back of the car. It's got the accumulator pack in yellow mounted ahead of that, and it's not a design I suggest you copy or any such thing, but it's just a visualization. Now I'm going to talk about how I would arrive at the situation to actually make this car, and at the end of it, this is in fact a real car, and at the end of it, I'll actually show you the finished car as it was built. Okay, as I've said, the only viable chassis solution for a new team is a simple space frame. The rules set some minimum dimensions for several tubes in the chassis. The main roll hoop and side impact structures and whatever. Now, there are arguments for and against round tube and square tube, but the rules require that the main roll hoop, for instance, should be round. But for a new team or an inexperienced team, I would be building the car from mostly square section tubing. Okay? There is a downside to doing this, and that is that if you have a look, a round tube of 1 inch nominal diameter is 3.15 inches in circumference. A square tube of 1 inch diameter is 4 inches in circumference. So there is about 20% more material in the square tube than there is in the round tube. Therefore, any given length of square tube will weigh about 20% more than any given length of round tube. And this would end up meaning that your chassis is probably going to weigh, maybe 5 kilos more if you make the majority of it from a square section tube. At this stage, immaterial, because the benefits to be got are huge. I've said on this slide here, square tube has less torsional stiffness than round tube, but it's better resisting bends, and it's easier to attach brackets to, and panels. If you were going to use square section tube right from the beginning, you would think now that the forces that I'm going to load into the chassis, I'm going to load the tubing in bending if it's square, and I'm going to load it in torsion if it's round. Try not to load square tube in torsion, because it will lozenge. It goes diamond shaped. It doesn't accept torsional loads very well at all. Okay. When you're mating round, you're going to do a round tube chassis. To do it properly, you're going to have to do something like this. That's lovely. But can you imagine the amount of work there is involved in making a joint like that, that's a joint there's 1, 2, 3, 4, 5, 6, 7 tubes arriving at a node there. And that is from a car. That's the main roll hoop, the vertical one. That's extremely difficult and time consuming to do. And if you don't do it properly, the weld is compromised and the structure ends up being neither as strong nor as stiff as it should be. The weld looks ugly. The judges look at it and they don't really like it. Whereas a square section tube, that one quick and dirty, but it's a similar thing. But you can see it's simply cut and shut miter joints. It's like carpentry. Much quicker, much easier to get the angles right, much easier to get the joints right. And in this case, it's just been MIG welded with a wire welder, and a much more suitable solution for an inexperienced team to be able to get this chassis done, built quickly. It's also more easy to jig up a chassis like this. Remember, when you're building the chassis, you're going to have to build it in some sort of jig. Otherwise, it will walk as you weld it. It'll just the things will walk around. And hang on, I'll just find where I'm in my notes. Yeah, we're getting well down there. Yeah. Okay. Here, I've actually got that's a picture of a Lotus Formula 2 car from a few years ago. And you can see that it's actually been made from a square section tube. And there's a little trick here that I can show you. That's something that they've actually done to save weight in the car. See this plate that's been welded in here that blocks that tube off? You just cut the tube and put a plate in there. That's because they use this tube here, or maybe this tube here, might be this tube here, but they use one of the tubes as a coolant tube to bring water from the radiator in the front of the car back to the engine in the back. Yeah, it's this front one here. That saves having to run extra tubes up and down the car, extra weight, so overcomes some of the weight. However, this is not just done in square section tube cars, because this is a Brabham race car, a round tube car from the same period. And you can see in this case, they're using this tube here to bring coolant from the radiator down to the engine, actually using the chassis tubes. That's the seat there, main roll loop, engine back here. And this is the chassis rail, main chassis rail, bringing water down to. So you see, looking at those cars from the 1960s and 1970s, when this type of car was the state of the art, you'll get a lot of really good ideas about structures and how you can do things, how you can build your little car that will make the judges and everybody proud of what you're doing. Okay, I said this the other day, but I'll say it again. I understand that there's a language issue in India regarding the use of the words tube and pipe. These terms are not interchangeable. Tube, described by diameter and wall thickness, is used for structures, and that's what you should be using to build your car. Pipe is used to transfer fluids, water or gases, air, whatever, and that's actually described by the inner diameter. So, you've got a half inch water pipe, might be 1 inch outside diameter, but the inside diameter is half inch. Don't use any of that on your car. That's not structural. That's not what you should be using to build your chassis. Now, I've said there's no need in your car for expensive alloy steels like 4130 chrome moly or any of those T50 special alloy tubes. The benefit that is to be had is that it's available in very thin walls. So in some areas of the car, you might be able to use thin wall chrome moly tube in some areas to try to save a little bit of weight. But this is not an option we need to either consider here. This is just don't even think about it. The downsides of chrome moly are it's difficult to weld, and it needs post-weld heat treatment, which I'll come back to in a minute. Good quality ASA 1018 or 1020 mild steel tube, perfectly suitable for what you're doing. And some of the best tubes in the world come from Tata Steel in India. Okay, 4130, I said, requires special welding techniques and post-welding normalization to avoid cracking in the has affected zone. We've seen many Formula student cars fail. They have a chassis fail in a loaded part of the chassis where a welded structure fails, not at the weld, but about 5 millimeters away from the weld, where some heat effect has damaged the structure of the steel. This is a classic failure. You can see the weld is good. However, the tube has failed about 5 millimeters away from the weld. Happens. Okay, time to start talking about how you actually build the car. Again, I talked about this the other day, that there are some cultural habits rife in India that you must overcome. You aspire to be engineers, not auto rickshaw fixer-uppers, so you're not going to go working around in the dirt like this. That's not how engineers work. You don't throw your tools in the dirt. You don't work on the dirt. You work in clean surroundings. Pick the car up. The car should be standing up on stands or at work height. You should have your tools on benches, easy to access, good access to the car. One thing that I've also noticed in India is everybody wants to help, so everybody crowds in, and the poor guys who are trying to do the work actually get crowded out, get starved of oxygen by 25 others who just want to help or want to see what's happening. You need to get the crowd to move back and give you a little space. Okay, here, this is how real engineers work. This is a race shop. It's not a Formula One shop. It's just a race team shop. And they're between races. You can see they brought the cars in. The cars are standing on stands. They've been stripped down. And you can actually see that on the closer car, one of the mechanics actually has a vacuum cleaner out, and he's actually vacuuming some dirt out of the chassis where may have picked up some dirt. And then you can see the layout is clean. Everything's clean and tidy. The cars are up on stands. The workbenches in the background are clean and uncluttered. Now, I don't really expect that any team in Formula Imperial is going to have facilities that look like this, but I would expect that you should have something kind of like this. At least the car is up out of the way, although I do wish they'd shut the drawer on that ready tool chest behind them before somebody breaks their leg on it. But that's sort of the minimum of sort of working conditions. Maybe clear this mess in the background away a bit more. But I understand, the constraints that you have, but you want to make sure that your workplace is clean, it's well lit, it's well ventilated. You need a surface plate or something like this that's worked on with some sort of jigging. You can see there are some jigging fixtures bolted to that plate to enable them to make sure that the suspension pickup points are in the right place. What I would like to see, and this is a number that I just want you to put in your head, but don't go quoting, but try to keep the suspension pickup points to within 2 millimeters of their design position, no more than that. If you get more than 2 millimeters out, you're going to have difficulty in adjusting the corner weights and the suspension geometry that you're looking for. The tubes themselves, they can be, maybe 4 millimeters out of place, but the actual brackets and suspension pickup points and so on and so forth, you need to assemble those with much more accuracy. So that's the stuff you need to jig. As I said, the main tubes, they can be just laid in place and tacked in place and then welded. Okay, starting with your chassis, the main roll hoop must be made from a single length of tubing, goes all the way from the ground on one side, bottom tube on one side, up and across the car, and down to the bottom tube on the other side. So I guess it's as good a place to start as any. The materials and dimensions for the main roll hoop are set in the rules, and they must be met, or the chassis will fail tech. Remember, you have to drill a little hole in this, so they will measure the wall thickness. Make sure that the bends are smooth bends; they're not crimped. It may actually be necessary for you to have the roll hoop bent up by a company who can actually do this sort of stuff, rather than try to do it yourself. You'll have people who'll tell you, just fill it with sand and block up the ends, and then you can bend it. It's not really that easy. But certainly you don't want crimps or wrinkling in the bend. You don't want the diameter to be pinched down. It's quite a It's quite a task to bend that main roll hoop properly. Okay. As I said, very important to maintain accuracy. And the various mounting points, a good target is to keep these points between, with plus or minus 2 millimeters. And the actual position of the tube's not so critical, so plus or minus 4 millimeters should be your aim. Okay. It may be easier to build a chassis in sections like this. So like you build the back bit and you build the front bit. What you got to be super careful about here, though, is that when you start to build the bit in the middle, you want to make sure that the back and the front stay in proper alignment with the rear. Otherwise, you've got a built-in twist or a built-in skew in the chassis before you've even started. Okay. In this case, the center section's been made. You can see the front roll hoop is here, and then it will all be welded together. I don't think I'd do it that way. I think I'd do it this way. I think I'd do it planar. In other words, build it in planes from the bottom up. In this case, we haven't started with the main roll loop, but the main roll loop will go in from this node, through that node, around and back down to this node here. Okay, connecting the front and rear chassis bays, how you go about it. There's no set way of doing it. You do whatever suits you. Yeah. Here we see in red the addition of the mandatory side impact members and the front hoop support members. They're required by the rules. Important that you do those correctly. And here we have the chassis essentially finished. Now, I'm not suggesting for 1 second that you should build this car. This is just simply an example of what you should be looking at building. You know, something like that. That's basically how you go about it. There's the actual car built. Not so sure about the wooden floor, but you know, that's actually the car has been built. It's not exactly the same as the drawings, but it's very, very close. Okay. Anybody got any questions? But we're not finished yet. I have some other things to show you, but I'll take a few questions if you wish. I'm waiting. Are we sure there are no questions? Surely somebody's got to have something they want to ask. Well, obviously not, so we'll talk about some other stuff. Said here that Formula Student cars have become very similar in conception. They're either a single or a four-cylinder IC car in a space frame or composite chassis, or an electric vehicle in a similar chassis, sometimes with four-wheel drive, and the occasional hybrids. There is a Formula Hybrid event in the US, but it's not really very successful. Building a hybrid car is very, very difficult because you actually all the problems of an EV car and an IC car combined in one. But there are some other solutions, some things that we don't normally see. So how about a front-wheel drive car? Now, there's nothing in the rules that says you can't have a front-wheel drive car. Most cars on the road these days are front-wheel drive. And it might be that a young engineer might think that he wants to graduate from Formula Student into a design job at Mahindra or Tata or one of the car companies. And so he would like to learn about front drive dynamics and engineering. And so he might choose to lead a team to build a front drive Formula Student car. I have no idea how it would go. This is not a Formula Student car. It's something very similar. But there is no reason why you couldn't build a front-wheel drive Formula Student car. I've never seen one, but There you go. Okay. What about this fella? Now, that's not a Formula Student car either, but we have had side-engine cars, or sidewinders as they call them, in Formula Student before, including some very successful ones. When you take into account Pat's third rule, that all things being equal, the car with the lowest moment of inertia will win, this car has a very low moment of inertia. If I were building a Formula Student car like this, I don't think I'd be using a multi-cylinder engine. I'd use a much narrower single-cylinder engine, a 390 KDM or something similar. Down chain drive down the right-hand side of the driver to a spool drive in the back, and away we go. I can promise you that would be every bit as fast as it looks. That would be a very, very fast car. Interesting little thing. This is how the professionals do it. A few years ago, Honda brought out what they called a hobby car. This was a little car for people to buy and take and garage at their local racetrack, instead of a racetrack, and they go out there like a golfer goes out and shoots, a few holes of golf. These drivers would go out, get into their little Honda racer, and they'd go out and they would do 20, 30, 50 laps or whatever, have fun, take it back to the garage and park it where it would be maintained and looked after by the mechanics there until such time as he came to drive it again. It's interesting that to build their little car, Honda chose the side-engined design. There's actually a drawing of it there, so you can see it's a little single-cylinder engine driving down into a differential in the back of the car. The argument, of course, is that the frontal area of such a car would be very big, but realistically, when you consider that the top speed of a Formula Student car is limited to, about 100 kilometers an hour, frontal area is not really that important. And that's about that for this time. You'll notice I have not touched on aerodynamics or wings at all. That's because, A, there was no place for them in this particular presentation. And secondly, it's a topic for another time and another place. Okay, one last chance if you have questions you'd like to ask. Yeah, go.
Hey, Pat.
Yeah.
Yeah, this is Himanshu. I have a question that what is your say on using a universal joint on a steering column?
Okay, I don't really have a problem with that. I know that somebody else does. We won't name any names, but we know who I'm talking about. A single universal joint driven through an angle is going to have a change in rotational acceleration as you steer the car. And that's not such a bad thing, because it could be that you could organize the joint in such a way that the steering is stiffest in the straight ahead position, but gets a little bit softer as the driver applies some lock. So when he's jacking the car, you could actually sort of a very low grade power steering, if you know what I mean. But I don't have a problem with it. If you have two universal joints, you want to ensure that they are clocked together so that the rotational inertia is cancelled out between the rotational acceleration is cancelled out between the two joints. Now, I don't have a problem with that at all. The other problem, of course, is that you need to support the shaft between the joints. Okay.
Yeah, thank you for that.
No dramas. More questions?
Yes, sir. So I actually have a question on aerodynamics of FSA cars.
I thought we were talking about aerodynamics. Yeah, go ahead.
Yeah, but actually I need to know, like, if you are manufacturing a car that has an average speed of
stop. Can you
Yeah.
slow down a little bit because I'm having a little difficulty understanding what you're saying?
Yes, sir.
Okay.
So actually, if we are designing a car that has an average speed of about 45 to 50 kilometers an hour,
Yes.
so is it worth having an aerodynamic kit with all diffusers and
No.
front and rear wings, all this
No.
stuff?
No. Simple as that.
Because from your previous presentation, I found that speed is not that important when we are building a car. That more reliability is the primary consideration.
Absolutely.
So,
Absolutely. The situation with wings is that there is very little benefit to be gained by fitting the car with an aerodynamic package. So unless you are actually running in the competition and scoring, say, 75 or 80% of the available points, and so you're starting to look very hard for small amounts of improvement, then maybe it's the time to think about what's happened here. Yeah, time to think about an aerodynamic package. But if you consider the problem with aerodynamics on a Formula Student car is that the plan area of the car is so small, and the length of the car between where the front wing goes and where the rear wing is very short. So if you take, for example, a Formula One car or an Indy car, Formula One car is a good example. They're really long, okay? So they have a great big wing at the front that generates a great amount of downforce, but also generates a great amount of turbulence. But you've got a long distance in the car to get that airflow straightened out and back under control before you reach the rear wing section to generate the downforce of the rear of the car. That's why they've got all the flips and wings and barge boards and all that other stuff that's down the side of the car to straighten up the airflow. We don't have that in a Formula Student car because the front wing and the rear wing are just there. Second thing is the center of pressure of the rear wing is well above the center of gravity of the car. So the drag on the rear wing is trying to blow the car over backwards. In other words, there is a weight transfer onto the rear axle, but away from the front axle. And you have to overcome that by putting a bigger wing on the front or running a higher angle of attack, which increases the drag and whatever. To gain what? To gain. Yeah. Second thing is that at no stage are you going fast enough. Remember that lift and drag are increased by the square of the speed. So twice the speed, 4 times the lift and drag, or half the speed, a quarter of the lift and drag. So when you're talking about in the corners, all the corners in a Formula Student event are slow. They're deliberately slow. We make them slow because we're protecting your health and safety. And that means that in the corners, the benefits of an aerodynamic package are very, very little. But when you get on the straights, like in the acceleration event, when you might reach 100 or 110 kilometers an hour, or if there is a decent straight on the track, all that does is huge amounts of drag, which slow you down. You may have actually saved, maybe half a second in the acceleration event if you had no wings on there at all. So, to me, wings are viable, but only when you are an extremely experienced team with a well-evolved, well-polished package, and you're really starting to look for that last little bit of performance. Does that make sense to you?
Yes, sir, I got it.
Yep. So we laugh, the judges. I mean, not in public, but we joke about many of the cars. The majority of cars we see with wings, we say the only download they've got is gravitational download from the extra weight of the aerodynamic package. The actual aero doesn't do anything.
So aerodynamics is mostly for it's not for FSA even. So accordingly.
No. I mean,
Yes.
most times it goes on there for aesthetics. That the team think, or somebody in the team thinks that it looks good. You know, you have at the design meeting, somebody says, "Well, I'll work on the engine mounting," and somebody else says, "Well, I'll work on the steering," and somebody else says, "Oh, I'll design the wings," because that's what he's interested in. But realistically, don't do wings. Use the time wasted and spent in trying to develop a wing package. You could be better off in getting the car finished early, getting on the track and testing, and getting that reliability thing that I said was so important.
Yes.
You got to get to the finish of the event. No team ever said, "Yeah, we'll go to Formula Imperial and we'll have a DNF and we'll pack up and go home early." Nobody ever said that.
Yes.
Okay.
Yeah.
Any more questions? Or have I put you all asleep?
Hello.
Yes, go.
Yeah, this is Himanshu again.
Yeah.
Can you please explain again the when we use a spool and there are the lengths of drive shafts are different on both the sides? How does it exactly affect the dynamics of the vehicle?
Look, not just a spool. With any car, whether you're using a differential or a spool, you should aim that the torsional stiffness of the rear axles should be similar. So if you have a rear axle assembly that's offset in the car, and one axle is longer than the other, that angle is that longer shaft. If both are the same thickness, will have more capability of storing torque than the short one. So what you might need to do there is perhaps cut that axle and replace the tube, the steel bar, the steel axle with a tube, weld a tube in instead, or something like that, so that they both have the same torsional stiffness. That's whether you have a spool or not, doesn't really matter what you've got. With a spool, the business of making a spool go around corners has got nothing to do with the ability of the axles to store torque or to give back torque. What we're talking about there was if you can imagine that with the car sitting on the ground, if it has say 100 kilograms of download on the rear wheels, and split equally across the wheel. So you've got 50 kilos of download on each wheel. Okay, now we arrive at a corner, the car starts to turn, and there is a lateral force applied, which causes weight transfer from the inside to the outside. This is correct, isn't it?
Yeah.
Yeah, okay. So let's say now that the outside wheel goes from 50 kilos to 70 kilos, and the inside wheel is still on the ground. We haven't picked it up in the air or anything, but the inside wheel has gone. What's the inside wheel? If we've moved 20 to the outside, what's the inside? Inside's going to be 30. Correct?
Correct.
Yeah. Okay, so we got 30 kilos of downforce on the inside wheel and 70 kilos of downforce on the outside wheel, and they're both subjected to a lateral load. Now that means that they're running at a slip angle. They're not running in the direction that they're actually being pointed. Now because of the vertical loads are different, one wheel is going to run at a greater slip angle than the other one. Correct?
Yes.
Okay. Now, the one with the least load is going to run at the greater slip angle because it's not gripping as hard. Correct? You got to think about
Correct.
that. Yeah, okay. Now, you can then fine-tune the actual slip angle by fine-tuning the static toe when you're testing on the car so that the car will turn by using the difference in the slip angles on the back of the car as, if you like, a differential within the car itself. Like a virtual differential, shall we say. Go-karts do it. And you've seen racing go-karts go around a track, haven't you? They don't understeer.
Yes.
They go. In fact, a 125 shifter cart would be faster around any Formula Student track than the Formula Student cars. Considerably faster. But yeah, so you have to understand that what now. Okay, so I missed out a bit too. So it's not just the weight transfer across the chassis. Remember at the front of the car, I said that the caster and the scrub radius generates a diagonal weight transfer. So that can cause something else. So instead of having 70 on the outside and 30 on the inside, we might have 80 on the outside and only 20 on the inside. So there's another area that we can tune the car by tuning the toe at the front or the Ackerman at the front to change the amount of diagonal weight transfer, because what we're looking at is trying to change the load difference across the rear axle so that the slip angles will allow the tires to run in the direction that you want the car to run to turn. Sounds complicated, but maybe you need to sit down and have a chat with your team about it and think about where it arises.
Yeah, right. It's just getting a little difficult to understand, but I'll just
as long as you've got the the gist of it. Once if you start to draw some force diagrams and look at what you're looking at, what we've just spoken about, and talk with a couple of other people, and it'll all come to you. Now it doesn't just happen, because what you have to first of all design that feature into the car, and then you have to get the thing on the track and you have to tune the daylights out of it and teach the drivers how to drive it, because the drivers need to be able to generate the lateral forces very quickly. In other words, they need to arrive at the corner and flick the car in to make it all start to happen. Otherwise, it will just plow straight ahead because the dynamics are not right to make the spool work. No one said it was easy. If it was easy, everybody'd do it.
right.
Okay. So if you want to talk to me about that at some later date, don't hesitate. I have an email address that you can write to me at. Easiest address in the world to remember. It's pat.clarke@email.com.
Okay, I will just contact you once I'm clear with everything I say.
Yeah, if you write to me, make sure you tell me who you are and what team you're with.
Yeah, sure.
Otherwise, there's no point in saying, "Oh, this is Pat." Or like, who's? Yeah, who are you? Yeah. Okay. Any more questions? It's 5 minutes to 10 here, and I'm going to go at 10 o'clock. So you have 5 minutes if you have some questions or any point of discussion you want to ask.
Yeah, I have one more question.
Yeah, go.
Throttle body of KTM 390 engine is having a diameter of around 42 mm, right?
Yeah.
So if we do not have a chance to get a throttle body with less diameter,
yeah,
what can we do to adjust it by using a restrictor? Can we do it with the help of restrictor?
No, look, not really. It's the whole system is designed that the software or firmware in the ECU measure with input from the throttle position sensor is expecting that the voltage signal on that throttle body goes from about 1 volt to about 4 volts, or it might go from 4 volts down to 1 volt. I'm not sure which way it operates. So, but if you fit the restrictor and don't just use the standard throttle body, you open the throttle, and by the time the voltage gets from say 1 volt to say 2 volts or 2.5 volts, now that's all the air that's going into the engine. Now, the ECU doesn't know how much air is going into the engine. It just knows what the voltage is from the throttle position sensor. So if you open the throttle even farther, what happens is that the voltage from the throttle position sensor goes higher. The ECU thinks that there's more air going into the engine. It gives more fuel to mix with that air, and it changes the ignition timing to get the optimum ignition timing for that engine to fire. But in fact, there isn't that amount of air. So the mixture goes really rich and the ignition timing is way off. Now, I've had a suggestion, and the engine, like I have seen an engine where there was so much fuel going through it that it washed the oil off the cylinder bore and the ring seized on the bore, so that destroyed the engine. I have seen teams where they have actually put a stop on the throttle to stop the throttle opening any more than about 1/3 of the way. They figured that full throttle was as much as the restrictor would allow to flow, and that's all they were going to get. The problem with that was that the throttle pedal moved about 3 or 4 millimeters from stop to full throttle. Well, how do you drive that? You know, the throttle in the engine becomes like an electric switch. It was either on or off, all or nothing. The driver couldn't drive the car smoothly. You really do need to adapt another throttle. And the one to look at is realistically is from the little one 150cc KTM, 125 or 150 KTM. It was very, very similar. The feedback, but the real problem, of course, is the logic in the ECU that's trying to control the fueling and the ignition timing. It's not as easy as you might think it is, but not impossible. There are teams that do it. Okay.
Yeah.
I'm sorry I can't give you an easy answer because there isn't one. It's that KTM is a very high tech engine. It's I don't know whether you're aware, but its compression ratio is 13.5 to 1, which is extremely high. And they use fuel and knock control, like detonation control, because it's got a knock sensor to prevent detonation, to stop the thing from destroying itself. If you get the fueling wrong and it goes lean, it will literally burn a hole in the piston while you look at it. Zap. We've seen or burn. The first thing that usually happens is they burn off the center electrode on the spark plug because they just go dead lean. They go into detonation and the engine will fail. So you do have to be gentle with them.
Yeah, right.
Okay. All right. It's 1 minute to 10, so I have time for one more question. Hello. Okay, well, it sounds like nobody needs to talk to me, so I'm going to call this quits, and I'm going to sign off, and it's 10 o'clock at night here, so I need to spend a little time with my wife and get ready to go to bed. Okay, thanks for listening. Nice to talk to you, and we'll do this again soon. If you guys feel that there is some other topic that you would like discussed or you would like me to talk about, let the organizers of the event know, and I'm sure we can organize another session, at some stage in the future. It's unlikely that I'll be able to attend the dynamic events in January because we still have COVID issues here, and there are no flights out of Australia for at the moment. I can't get out of the place. We're all locked down. You are aware that I'm based in Australia, based in Sydney. So, but it's my intention that the next year's event, which I understand will be held in July or thereabouts, I fully intend to be there and meet up with you all then. Okay. Good night, all, and thank you for your attendance and thank you for your attention. And I hope it was a good night for you, and see you then. Bye-bye.
Thank you, sir. And thank you for your valuable words. And I hope that Formula teams will implement your ideas that you have shared with them in this webinar.
It's their choice
And
if they choose to do so.
yes, sir, sure. And we already informed you about the registration of Formula Imperial 2022. So
Yeah.
we will hope that you will present in at the time of event for the competition. Thank you, sir.
Okay. Good night. Thank you very much. Talk to
Good
you
night.
soon. Bye-bye.